Hello and welcome back to Calculus 1, section 3.7 on chain rule. So this is the most used derivative technique. About 90-95% of derivatives you take from this point on will be chain rule. So let's learn all of this. We start with function composition. So function composition is taught in pre-calculus, and it has to do with plugging one function in another function to create a third function that will have its own domain, range, and properties. So we have two functions, some f of x and some g of x. And what we do is we create function composition. The symbol in the middle is actually open circle. It's not all. It's open circle. You know how you will say f times g and you put a little dot? Well, this is the open circle between the two functions. So f composed with g of x, which means plug g inside of f, where it used to be f of x. So you see that you are supposed to replace every x with g of x, right? That's what we are doing. And you can also compose g with f, where g is the boss and f is plugged in. So this is technically a story of a backpack, right? Where the purpose of the backpack is technically defined by the content of the backpack, whether it's a camping backpack or the one with the parachute or the one with the books, right? Or the clothes, where if you're going somewhere overnight, just put a backpack with one change of clothing and toothbrush and just leave. So the content, which is the function that it's the second function, right, is plugged into the first function, which is always the backpack. That will be that kind of thinking. So now, if we have that f of x is equal to x squared plus 3x minus square root of x plus, let's say, 4 over x, and g of x is equal to sine x, we can calculate the function composition of f and g, where f is what I call outer function, boss function, would be sine squared x plus 3 sine x minus square root of sine x plus 4 over sine x. So please immediately see that if you are to replace every sine with x, you will have exactly just f. And we can also compose g with f and create sine of, and now replace x of g with the f, which would be all of this. So this is how the function composition works. Now, unfortunately, that's not the skill we need. We need the skill of decomposition. And that is not something that is taught in pre-calc 1, and it's opposite of this. And that's the skill we need. So let's talk about function decomposition, which is what we actually need for our chain rule that's coming up. So decomposition. Say you have the function y equals e to the sine x. It should be clear by looking at this that you have function e to the x lurking around and sine x. Do we all see that? E to the x and sine x? Good. So now I need to look which one is the outer function, the boss function, the backpack function, whatever you want to call it, which is f, and which one is the one that it's plugged in, the contents of the backpack. So now when you're looking at this, which function would you say is the one that it's the main function, which one is plugged in?
E would be the main function, sin x would be plugged in.
Yes. So this would decompose into f of x is equal to e to the x, and g is plugged in there because this sin x, you see that there is x after sine, right? So this whole thing here goes into this x and creates e to the sin x. So, and we will always do f composed with g as we are, so that's the only one we're working on. So f will always be the main function and g will always be plugged in. So there is no deviation there. Now, y equal sine e to the x. What's f? And what's g? Anyone?
It would be the opposite, right?
It will be the opposite, exactly. Sine is the main function, sine x, and e to the x is plugged in. Because as this x in sine is replaced with e to the x, you get the function. Next one is what? Let's try y equal 3 square root of x squared plus 9. So now we have f of x again, and we have g of x. Any suggestions? Yes?
X plus 9.
Nope, unfortunately. Like when you start looking at this, just ignore 3 because you know that's going to end up being with f. So if you're ignoring 3, you have 2 functions to consider. So what are the 2 functions you are considering in this case? But see, a square root and x squared are immediately 2 different functions, right? Do you see that this x squared plus 9 is plugged into the square root? Like this could be one thing. This could be sine, it could be log, it could be anything. Do we see that? So it has to be 3 root x because that's the basic function. Root x is a basic function. This is x squared plus 9, also basic function, polynomial. Seems that this one was a bit tough. Tough to see.
I guess it's just like confusing that the same variable is used, like the x squared and the x is used to represent the x squared plus 9. You know what I mean? I guess.
Well, see, in the notation, so start this problem. So you can, because we will be taking derivative of this. If you can't decompose it, it's a problem. let's start with this. You have f of x. And let's say f of x is square root of x. And you know that you can draw the graph for square root of x. And then let's say that you have another function, g of x, which is, say, x squared plus 2. X squared plus 2 is also a function that you can graph here, right? So they all have input x. Now, if you have your f of x as root x, and you say f of 3, you are getting square root of 3. If you say f of 5, you are getting root 5. F of a flower, that's a terrible flower. F of a flower, that's better, I guess, is a square root of a flower. So if I have f of g of x, then it's square root of g of x. So that's why the variable is the same. But you have to understand that you are taking out this x, literally deleting it, and you are plugging in the entire function g of x. But what is g of x? G of x is all of this. Then you say, okay, let me replace that now with x squared plus 2. Does it make sense?
Yeah.
Okay.
The concept is fine. The notation is just...
Yeah, the notation is, yeah, okay. So as we are working on a function composition, you can always see that the backpack, what I call the backpack function, right, the main function, the boss function, always gets this x, like out of nowhere. Well, it's not out of nowhere. It's actually, this whole thing was an x. This is an x. And this is an x. Right? Those are all x's, which are this x, and this x, and this x here. That's what they are. So you have your e to the x, which is e to the x, sine of x, which is sine of x, and root of x, which is root of x. Perfect? So, I mean, obviously every problem is doing this. So we'll have plenty of practice to decompose. Good. So finally, we can do some chain rule. We do motivation for chain rule first. Obviously, the derivative of x squared is equal to 2x, and we have nothing to worry about, right? Now, if you have x minus 3 squared for the derivative, well, the only way you can do this is to square this and get the derivative of x squared minus 6x plus 9, and then you take your derivative as 2x minus 6. So this is what you know so far. And then we have x minus 3 raised to the power of 27, right? And then you go, really? To FOIL this to the 27th power? Right? That will take some time. So is there a better way? And the answer is yes. Chain rule. This is a composite function where f is x to the 27, that's the outer function, and g is x minus 3. So yes, there is a much better way to deal with this derivative than foiling this exponent of 27 and then figuring out the derivative this way. See, when the exponent is small, like 2 or 3, yeah, you might want to foil it, but you shouldn't, but you can. But you know, anything bigger than that, obviously, chain rule is your buddy. So what is the formula for chain rule? Chain rule is taking the derivative of function composition. And the derivative of function composition, the answer would be f prime of g of x times g prime of x. Now this is a formula that we use to get the chain rule. It's one of those very, very, very important forms. Put this on a cloud. And what do we have there? We have, as you can see, f, and then we have the g. So this is where the chain, right, kicks in. This is what we call the chain, that g prime. So now, if I am trying to find the derivative of x minus 3 to the 27th power, and I know that my decomposition is f is x to 27 and g is x minus 3, see, immediately this line here is labeling this as x to the 27. So what is the derivative of x to the 27? It's clearly 27x to the 26. That's what the derivative is. But if you look at the formula is requiring you to put g of x in there. So this part is x minus 3, the same one as you had here. And then the chain rule kicks in, and we have the derivative of 1, which is derivative of the inside. This is the chain. So we were able to quickly come up with the derivative with the exponent of 27 without foiling anything. So one more time, as we decompose this in our head into these guys here, we see that the main function f is x to the 27. Derivative of x to the 27 is 27x to the 26, but then it's not going to be x. It's going to be whatever the g of x is, so we plug in x minus 3 there. And then we follow by the derivative of chain because it's times g prime. Let's do about 10,000 examples. The derivative of sine of x to the 5 we had this exercise before for decomposition. We know that f is sine x and g is x to the 5. That is something that should be clear from our decomposition. Now, to take the derivative, I say the derivative of the outer function, right, is of sine x is cosine x. But I don't get to write cosine x. I get to write cosine of g. Cosine of g, which is x to the 5, times the derivative of x to the 5, which is 5x to the 4. That's the chain. For the total of 5x to the 4 cosine x to the 5. Formula that you're familiar with, e to the 3x. You memorized the answer for this. Now we get to actually do it. We have f to be e to the x and g to be 3x, right? That's the decomposition. So what's the outer? Derivative of e to the x is e to the x, so e to the 3x, times the derivative of 3x is 3, which is exactly what you memorized before. A, e to the ax, right? There's that a that goes outside. It's a chain rule. The derivative of 2 square root of x cubed minus 1. Well, we can rewrite this as 2 x cubed minus 1 raised to the 1/2 power. The trick, as you can see over here, is always that whatever is inside, whether it's single, like 3x, or multiple terms, like x cubed minus 1, is to group all of that together on a pile, and you immediately get your, actually I should have grouped it this way. Group it on a pile, and you immediately have your outer function, which is 2x to the 1/2. So this is equal to, now, the derivative of the outside. So that's 2 1/2 x cubed minus 1 to the negative 1/2 times 3x squared. So what do I have? The derivative of this drops a half down. Those are the exponent ones, right? So drops the half down, and then 1/2 minus 1 is negative 1/2, and this was supposed to be x, but it's actually g, so we have to put x cubed minus 1, times the derivative of the inside, and that's the chain, right? So the derivative of the inside, as I say over here, that's the chain. I labeled it on the previous, yes I did. For the total, these halves cancel of 3x squared divided by the square root of x cubed minus 1. Because negative 1/2 is going to push in the denominator, half is the root. So negative pushes down and the square root is given by a half. So we always try to see what part of the function is g and what part is f. And as soon as you realize that this is g, in your head you try to compress it into a single variable and you say, what is the derivative of just 2 root x? But instead of writing x, you write g. So then you replace g, and always there is a chain, the derivative of the inside. So when you go back, right, you say, okay, this was not a basic function, so let me put the derivative there, and there it is. Derivative of x to the 6 minus x plus 1 raised to the 4th power. Try this one on your own. Okay, so we have our f to be hopefully 3x to the 4, right? I hope we are all okay with that. And then g is the guts, right? The inside. X to the 6 minus x plus 1. So now we take the derivative of the outside first, which would be 12x to the 3. Please look at the screen as I am writing this. The derivative of 3x to the 4, 4 drops down, 3 times 4 is 12. Look the way, as I am saying it, look the way I write. That's the key part. I say 12x to the 3. Because I'm leaving part here to put the g in. I said x because I'm looking at x. But I left space for g. Because the formula is f prime of g times g prime. That's the formula. So 12x cubed, and instead of x, I write g, times, and now the chain, 6x to the 5 minus 1. And you have to put that in parentheses because you have two terms there. They both need to multiply the one in front. And you are done. E to the x squared plus 6. Let's see what you come up with this one. What is f? E to the x. Beautiful. What is g? X squared plus 6. Great. So the derivative of e to the x is e to the x. So you get to copy the same thing, right? Derivative of e to the x is e to the x. So you get to copy it as is, times the derivative of the inside. So the total is 2x e to the x squared plus 6. That's all it is. Let's take a look at a few homework examples. Okay. Problem 47 was your log trig. Says find the derivative of 1 plus 2 tangent x raised to, now they say 4.5, and let's just do 4. 4.5. Why? It's just 4. 4 is fine. What is f?
X to the fourth.
X to the fourth. Perfect. What is g?
1 plus 2 tan x.
Everything else, yeah. So we have 4x cubed. 4x cubed. But as you can see, I didn't put x, I put space for the entire g in there. So 4x cubed, and then times the derivative of the inside. So that's 1 plus 2 tangent x And now what is the derivative of the inside? Derivative of 1 is
0.
0, so we don't have to worry about that. Very good. And what's the derivative of 2 tangent x?
2 secant squared x.
Beautiful. Right? Now we're going to simplify this into 8 secant squared x times 1 plus 2 tangent x cubed. That would be the form to present. Problem 46 has more trig because I know you love it, right? How about cosine x plus 2 sine x, everything to the 8? I'm sorry? Like this? Well, you're welcome. Wow, I'm so accommodating today. I'm going to mark calendar.
Too hard to peel off, right?
Yeah. All right, so what is the outer function f? x to the 8th. Very good. And the inner function g, then it's the cosine plus 2 sine, right, in the inside. Very good, very good. All right, so now we have the derivative is 8x to the 7. So we plug in cosine x plus 2 sine x, right? And what's the inside? The guts. The derivative of cosine is negative sine x, very good, plus 2 cosine x. Very good. All right, great. All of these examples, we practice the basic idea of the chain rule. Yes? What, you mean doing the arrow like this, or? You can draw the arrow, it's fine, yeah. You mean, oh, well, when you can simplify, there's nothing you can do here, right? When you can, sure, nothing you can do here. Over here we put 2x in front because generally we like the constant and then just bring the x as well, right? So when you can simplify, chapter 4 is coming, right? The winter is coming. So the chapter 4 is coming up, and you will say equal to 0. So you really don't want to, right? This will be just a first step. You take the derivative in the margin, and it's a chain rule. So as chapter 4 is approaching, you want to have your answers simplified, factored, you know, in the cheapest possible form, so that you can say equal to 0 and then go and do stuff from there. So what do I want? No, nothing. Technically, I want nothing. But, you know, there are things, because this is already cool form, the one that it's given. Because as you said equal to 0, you have 8 equal to 0, no solution. This parenthesis with the 7th power equal to 0, well, 7th power doesn't count, so it's just the guts equal to 0. And the last one is also equal to 0. So if you look at the, let's say, last one in chapter 4, saying sine x plus 2 cosine y, cosine x, sorry, equals 0, you move sine to the other side, and you get eventually tangent x equals 2. And you hit the inverse tangent, and you have x equals, and that's going to be a critical point. And then you go min, max, and things like that, right? That's chapter 4. So you want to have this in the simplest possible form so that you can solve the rest. Yes? Goes away. Let me check. All right. Should we start with the interesting things? Let's say, can you make this worse? Of course. That's why I'm here, right? How about nested chain rule, right? Let's think about this. Derivative of 3 sine to the 4th x cubed. How many functions do I have on a pile now? 3. Very good. I have 3 functions on a pile. So FGH? Sure, FGH. Now, another $1 million question. is what is the exact order. And it's kind of tough to see it, but let's do it anyway. What do you think is the... now, these ones are actually the best. When you see 3, 4, 5 functions on a pile, I think it's best to kind of work your way backwards. Like, okay, this is the last function, and this one is one before and one before. But you can also work forward. This is the boss function, right, the backpack, and then these are the things. Because you have, let's say, you are going to the trip, and you have the backpack, but then you have the smaller thing that keeps all the, you know, bathroom stuff, like a toothbrush and things. So you put that inside. So there you go, 3 layers now. So I think that age is obvious. What would be the age?
The smallest one?
Yeah. That one should be obvious. Okay, it's not working that way. Fine. Let's think of this way. If I'm to say x equals 2, how would you compute this? Like, what would you compute first?
That would be x to the third.
Aha. So that's the lowest level,
Yeah.
right? So you can think this way as well. What would be the first thing to calculate if I had x? That immediately reveals the lowest level, which is x cubed. Great. Now, you computed that. Now, what's the next thing you get to compute? You got your x cubed is 8. So now, if I'm to say, okay, this is now 8. What is the next thing that I'm computing? And this is when pre-calc kicks in.
X to the fourth?
See, the fourth has nothing to do with 8. It's not 8 to the fourth. Right? Now, this is where we have to go and review a little bit of the notation. And I'll put this in blood, right? In red. We have sine x, and we walk away. We also have sine squared x, which is the same as sine x everything squared, and the meaning of that is obviously sine x times sine x. Are we agreed on this? And then we have sine x squared, which is sine x times x. So these 3 lines are different from each other. So now when you are considering our problem up there, you can see that you can rewrite that problem as 3, open parenthesis, sine of x cubed to the 4th. And that is the skill that you must have to survive Calc 1, especially Calc 2. And also, the same notation works for ln. So I'll write that in blue. Same for ln x, because that's coming up later in this, later today. So now, as I am decomposing this function, x cubed is the lowest level. The next level up with the g would definitely be sine x.
Okay.
And then the top layer is 3x to the 4. So please meditate on this for a few moments to make sure that it makes sense. sine to what? Sine to the 4. Well, it's chain rule. Sine to the 4 is the chain rule because the sine is plugged in with the 4. So, yeah, you can. And we are actually going to do it here. That's where it gets decomposed. Anything raised to the exponent immediately creates a second function for you to do this kind of thing.
But for the g, it's like you left it before. You wouldn't make it before for the g.
No, because it's composite, right? We have to decompose the basic function. And sine to the 4th is not a basic function, it's a compositional function. So these are only allowed to have basic functions. Basic polynomial, basic trig, another basic polynomial, right? Or e to the x, or ln x, right? You are only allowed to have basic functions in there. So now what? Well, the derivative is going to be equal to, we do the 3x to the 4th first. That's 12x to the 3. X is going to be sine of x cubed inside, because that's the inside. See, this inside has to match this inside, because that's the interior. If we are replacing this with x to do the basic calculation, then that's your x in the result. That's what it is. And then we can now focus only on this. I don't need to see the rest of the problem. I don't need to see the rest of the problem. Now I know that I need to go and do the chain, which is the inside. Now the derivative of sine is cosine x cubed, and final chain here is 3x squared. Now that I have this, look what I'm going to do. Please look at the screen. 1, 2, 3, 1, 2, 3. This needs to be followed at all times. If I have 6 functions on a pile in a function composition, I will have 6 of these factors at the end. So 1, 2, 3, 1, 2, 3. Before that, it was 1, 2, 1, 2. For all of the problems we did, it was 1, 2, 1, 2. Now, we had 1, 2, 3, 1, 2, 3, so 1, 2, 3, 1, 2, 3. Can you make this prettier? Sure. 36x squared cosine x cubed sine cubed x cubed. That would be the prettier version of the problem. E equals to 0 for chapter 4, solve each one and you're done. These are called nested chain rule, where you have multiple functions, more than 2. How many can you have? As many as, yeah. Hopefully not 18. You know what I mean? Yes.
So you see how you know, in the first one that you did the derivative of, and then you like took the nested one out and popped it over there. You just kind of skipped that nested step for the second one, right? You just went straight to the. I mean, you skipped it because it was like self-evident, but like there could be something nested in there in the second one.
Yeah.
The third derivative.
Mm-hmm.
Okay. Okay.
Well, that goes from here, right? 1, 2, 3, 1, 2, 3.
Yeah.
Because a student asked me before, why do we stop? How do we know when to stop? Because technically the next one is 6x, and then 6, and then 0, and then 0, 0, 0, right? Well, in that case, every derivative pretty much would be 0, right? So this is why I did what I said with what I did in pink. I said 1, 2, 3, 1, 2, 3, stop. because there is, you know, if that was not the case, then there is nothing to stop you from saying times 6x, times 6, times 0. And as soon as you say times 0, because they're all times, 0 kills it all. Yes. Then every chain rule would be just 0 every time, right? So we have to stop. We have to stop. And we stop when we match the number of factors we have here. So 1, 2, 3, 1, 2, 3. That is the part. Yes? Because it's everything that, see, if you look here, right, x cube is in the inside, right? The cube is also the part of the whole thing. So I'm only taking the derivative of the outer shape of a function, which is to the 4. So the 4 goes down, makes it a 12, and changes it into a 3 over here. The dots stay the same, so it has a cube, right? This one over here is more function decomposition to say, oh, I have 1, 2, 3 of these, I will have 1, 2, 3 at the end. To know when to stop. F assumes both of these combined in there. So that's why this cube is there, because you have to take them. It's always, as you can see, I underline and I put the arrow and I say chain, because you are chaining the whole thing. So this is still a unit. And then that unit gets broken here into 2 parts. So now this is a unit to go forward. Now we'll do more examples, obviously.
I'm sorry, can you repeat where you got the cosine x?
That is the underlined, that's the underlined, let me just erase these now.
So you're not taking actually the g prime of g, it's actually...
Well, now the formula is modified now. Because you are taking the derivative of the function composition that it's f of g of h, because now it's a composite between 3 functions. So the derivative of this is f prime of g of h of x on the outside times the g prime of h of x times h prime of x.
Okay, that's what I was saying.
So yes. So, and you can see the g of h over here, which makes sense that to have that. So now, is this the final formula? No, because if I link another one in there, then I have to move everything for one more step. So we used the wow. So we used f of the derivative of f of g of h of x as f prime of g of h times g prime of h times h prime. Now, if you are to carefully examine this, you would see your old formula right there, which actually is exactly this much, right? So we technically are just nesting another function and another function, and this can be expanded into, as I said, as many functions as you want. So now, is this extension hard? No, it's just annoying. You're just having another layer, like onion, right? Layer, another layer, another layer, another layer, and you keep peeling those off until you get to the most basic function. So it works for any number of nested functions. The beautiful example in a textbook, in my humble opinion, right, is the sine of e to the x. This is problem 53. What is the derivative of sine of e to the x? How many functions do we have? 3. Very good. So we have our f, g, h again. Now, what is the first, second, third? What do we do?
Sine x would be the first.
Sine x would be the first. Perfect. How about the second one? Sine x again. Good. And how about the third layer, the core of the onion? E to the x. Very good. Here we go. The derivative of sine is cosine with sine e to the x as its inside times, now we go the chain, the derivative of sine of e to the x is cosine e to the x, and finally the derivative of the inside is e to the x, and there it is. And that's another chain. Does this make sense? Should we do another one of these composite ones? Let's do another one, yeah. I mean, it's Saturday, it's raining, and what else would we do, right? Imagine the alternative still being in bed. I mean, terrible, right? So, and I've been up since 4:30, so, you know, for me, day is almost over.
What do you do at 4:30 in the morning?
Anything I need to, it's, trust me, you'll have things to do if you get up at the time. We can talk about it later, but yeah, getting up early in the morning is something that I discovered about 5 years ago or so, following the example of my neighbor, and my productivity in life doubled. I was already productive at that point. Now it's doubled, and I'll talk to you later about it. So since you want another nested case, you're going to love 49. Find the derivative of square root of 1 plus cotangent squared x. Let's take a look. What's the outer function f? This one is tricky to decompose. Square root of x is perfect. Yes. And now for the $1 million. What is the g? Yes! 1 plus x squared. Because cotangent is plugged into the square, right? This is 1 plus something squared. Call that something x, and then later it will be cotangent x. So 1 plus x squared cotangent x. Okay, so now that we resolved that, I'll give you some time to try and fix the derivative. This is the toughest part, to figure out what goes where. With computing the value. So say x is equal to 2. What is the first thing that I will compute, and that goes on A's level, on the bottom? The first thing you will compute if x is equal to 2 is cotangent 2. Because the square has to be applied later, because we learned for trig functions that the square would go on the outside, right, as a right. So write PEMDAS, parentheses first. If I say x equals 2, the first thing I'm computing is actually cotangent, only cotangent. So cotangent would give me a value. And whatever that value is going to get squared and then 1. And then the root at the end. So that's the only other way that you can unwrap this. It's fun to try. Nice one. I support it. Let's take a look at this problem together. The derivative of square root of x is 1 over 2 square root of x. I'm going to replace that x obviously with the inside, which is 1 plus cotangent squared x. So you might want to write that as pretty much as a formula, so you don't have to mess with the 1/2 and subtract 1 and all of that. That the derivative of square root of x is 1 over 2 root x as a shortcut, pretty much. Square root x is a basic function that we know and memorize the graph for and all that, right? But for the derivatives is not that special, because it can be rewritten as x to the 1/2, and then you can use the x to the n formula to get it. But if you have to annoy yourself every time with using that formula, and you're going to see a lot of root x's around, maybe you just want to memorize the rule for it, and then always write the simplified version right off the bat. So now on the next one is I'm going to take the inside over here and do the chain. The derivative of 1 is 0. And the derivative of x squared is 2x, so I have 2 times cotangent x. So that will be the next one. And finally, the derivative of cotangent is negative cosecant squared x. Now, I'm going to show you why I love mathematics. All right, this is really personal now. The same problem 49 done in blue. If we use Pythagorean identity from pre-calc 2, 1 plus cotangent square is equal to cosecant squared x. And then the square root and square will cancel. Therefore, the derivative of cosecant squared x is negative cosecant x, just because they cancel, is cosecant x, cotangent x, and I just walk away. I know, right? The beautiful thing is sometimes you can use something that you learned a long time ago, if it's still, sticks around, and then some of the the problems you can just make. As soon as I saw the problem in a textbook, it was immediately like, wow, really? That's really something. Now, the blue immediately tells me that the black on top can be simplified. Now we immediately see that 1/2 and 2 cancel, and having the 1 plus cotangent would become that cosecant square, kill the root, and then that secant in the denominator would kill 1 secant over there. There you have a minus sign. Yeah, it does simplify into negative cosecant x, cotangent x. It does simplify. Again, how? This cancels the 2. The under the root, you have secant squared, cosecant squared. The square and the root cancel, so it becomes cosecant. Cosecant kills the cosecant here, and all you left is negative cosecant cotangent, which is what we need. Wow, right? Awesome. Ready for the next step? No, please no more. Yeah, you remember how we had the product rule and the quotient rule? Why not toss them in a mix as well? So we have a product rule within the chain, chain within a quotient, quotient product within a chain, chain within a quotient, and a product. It's called mathematical gymnastics, just because we can, all right? No, I'm saying that, you know, there are no applications that we use it, but a lot of problems in a book that have that. 52, 58, 60 is absolutely terrifying. Problem 40. So plenty examples in a book that have these product rule and quotient rule combined with this. Is it hard? No. Is it annoying? Yes. Right? I have to learn the difference between hard and annoying. So, what do I have? I have a simple problem of the derivative of, maybe we should label somehow these, whatever. Call it mathematical gymnastics now. I should define that as a field. How about x squared sine cubed x? So as you are looking at this problem, does this appear as a chain rule, product rule, or quotient rule at large? Right? If you're looking at the whole thing as a problem. Is this product, quotient, or chain? What do you think? All of the above. Well, definitely no quotient, right? Because there's no division. But we can see the traces of product rule and the chain rule. So what do you think would be the main one, right? Because you can't have them both at the same time. You have to do one first and then the other.
Separate x squared and sine 3x.
Okay, so and they're set in the product rule. So would you do product rule first? Because you know that sine cube is a chain, right? That's obvious. So do we have a product rule as a main or chain rule as a main in this one?
Start with the chain rule?
No. We have to do the product because the entire problem is one function times another function. The product rule must take precedence here because we have one function times another function. So I'll put the red dot in here to make sure you know there is a time. Just wanted to see if I can hit the same spot. So this is the product rule. Copy the first, derivative of the second, that's when the chain kicks in. Copy the second derivative of the first and you're done. So we know that the product rule is done by saying copy the first, which is x squared, times derivative of the second. That's going to be 3 sine squared x times cosine x. That's your chain. Plus copy the second, sine cubed x times derivative of the first, 2x. I'm going to label now this u, v prime plus v, u prime. Now, if you are not certain because you just learned it, how to deal with the chain part, you can do that on the side and then bring it back into the problem. So the entire problem was product rule. This is product rule with chain rule inside. If you want to try this differently, we can. d dx equals to x squared sine x raised to the 8th power. I hope you can see the difference between these two problems. The 8 is on the outside and you have a product of two functions inside. As soon as you stuff something inside something else, it's immediately function composition, so it's chain rule. So for the bottom problem, product rule is stuffed inside the chain rule. So what's the main one? Chain rule is the main one. Now, when you have to take the derivative for the chain rule, it will work out to be a product. So these are, again, trickier, but, you know, through time it gets better as you practice. So this is 8 times x to the 7th times the derivative of the guts. This is the setup. This is the setup because it's chain rule. You have this x squared sine x stuffed inside x to the 8th. And now, when I'm taking the derivative, this would be x squared sine x because that's just a standard chain rule. And now when you have to take the derivative of the inside, you realize, oh, that's a product rule. So now I have to go and say, copy the first, x squared, derivative of sine is cosine x, plus copy the second, sine x, times the derivative of the first, 2x. So they will be very good for you to study these two examples side by side and take a look which way the functions are. And ultimately, I mean, you have to understand the difference between, you know, function composition, function multiplication, and function division, obviously. So this problem, this is chain rule with product rule inside. One of the main things to learn from here is that when you look at any of the three formulas we covered, product, chain, quotient, they always have a time when you take the derivative. And that could be whatever rule. So if we are to write these three formulas now on the pile, starting with product rule, say, let's use F, right? F and G. It's F, G prime plus G, F prime. Note that at some point you are taking the derivative of G, you're taking a derivative of F. Or the derivative of F over G, which is GF prime minus FG prime over G squared. Again, we took the derivative of F, we took the derivative of G. And then we have our derivative of F of G of X, right? Which is F prime with G plugged in times G prime. Again, derivative F, derivative G. So the rules could be anywhere, right? I could have a product rule. I could have a product rule in here. If I have a product rule in here, then the product rule formula will kick in when I have to take derivative of F. The rest has nothing to do with the product rule, because the second term is copying F. If I have a chain rule, let's say for G, well, that would kick in here, chain rule for G. It's not going to kick at the G squared because I'm not taking the derivative there. It only kicks in when I need to take the derivative of product rule, quotient rule, chain rule. So, you know, that's the skill that is developed over time. Please don't get frustrated that your, answers are not working out within the first, 5 seconds. I went to a really brutal high school back in Serbia, and one thing that I will never forget is the answer of my math teacher to a fellow student, my friend, who asked a question in class and said, but I don't really understand how, and teacher said, you are not supposed to understand right now. I just taught this, right? If you knew this, then why are you here? So when you go home and you do 100 examples, it will be clear. If it's not clear, let's talk again about it, right? So, don't give up immediately. It's too much, it's over. I warned you that the chain rule section is going to be living hell, right? Welcome to hell, right? So now, start slow, right? Don't go immediately into, the homework and trying to solve MyMATLAB and everything like that, right? You want to build it up. You want to make sure that you can do the basic chain rule with 2 variables, and you keep doing that until you're bored, and then you do one more example, and then you bring the next layer. Let me, the same way I taught it, because I slowly crank the heat as we go on, right? We did whatever amount of examples over here, 6 or 7 examples with 2 functions only, right? And then we did 3 examples with 3 functions. And then I pushed in and I said, all right, but we can also have a product rule within this. So don't go and try to do, problem 63, right? Which has the nested function on the product rule with the chain rule inside, right? Because obviously it will be overwhelming. And as I said, you can't really do calculus monkey sees, monkey do, because it's just so many different functions, so many ways to combine them. And the argument of, I haven't seen a problem like this really doesn't fly. So not in calculus. It does in algebra, but not in calculus. So as you go layer by layer, right, you should be able to unwrap this and get it. So let's talk next time if you have more questions. Yes? No, there was not sine times sine. There's sine of sine. So you have to understand the notation, the difference between sine x times sine x, which is a product rule, and sine of sine x, which is a chain rule. See, this one had no sine. So this sine had no x. This sine has this as the argument, and this sine has x as the argument. These are two completely different things, and maybe that's something again worth noting here. Let's do that in, how about orange? If I have sine x times sine x, that's the product rule. And sine of sine x is the chain rule. Again, the reason is the second problem, the one on the bottom, has entire sine x as its argument on the first sine.
The f prime of g, is that equals g prime? The last blue one?
It's the product rule for g prime, g times.
Oh, time. Oh, I thought that was equals. I'm like, why is that equals? Okay.
It's times, yeah, times. Okay. It's called passion, as you write, right? You make the times look like a 9. There you go, great. All right.
Thank you.
Well, that's it. We're going to take a break. And then when we come back, we get to use this stuff. Next lecture is called implicit differentiation, which is chain rule 100% of the time for every problem that you see. See you then.